All right, so this is day 2 of section 3.6, derivatives of logarithmic functions. Derivatives of logarithmic functions. So let's kind of recap what we did yesterday. Yeah, let's kind of recap. Remember that the derivatives of logarithmic functions are, the derivative of log base b of x is 1 over x ln b, where b is just any base. Base 10, base 7, base 2, 1 over x ln 7, ln 2, ln whatever, ln 10. And then if we said, okay, what if I make that base e? What if I make that base e? So that would be 1 over x ln e, but ln e is just 1. So then we came up with this generalization where if you find the derivative of ln of x, it's just 1 over x, 1 over that thing on the inside. And then if we said, well, what if there's a chain rule? Well, then you just multiply by the derivative of the inside. So then we generalized it to saying, okay, the derivative of the ln of a function is the derivative of the inside divided by the original. Derivative of the inside divided by the original. And that's really where we were at, okay? And now we're here. So that was the derivatives of logarithms. You've learned pretty much everything you can learn about the derivatives of logarithms yesterday. What we're looking at here is actually a really cool, my version of cool, really cool way to find derivatives that I had to have learned it. I took calc. I took a lot of calc. So I'm sure I learned it somewhere along the way, but I remember thinking, wow, this is really neat, and I've never even used this before, and I kind of forgot about it. So it was pretty interesting. It's called logarithmic differentiation. Hi, how are you doing today?
I'm good. I have a opportunity for Maxwell. Oh my
Maxwell.
God.
Maxwell. No, you're just gonna keep the swap.
They had me keep it last time. Yeah.
No.
Thank you. I don't believe it.
You too.
Junior Cal.
Well, yeah,
We sent it to Douglas.
Hi, is there Maxwell in the room?
They said they sent
Can I just call you Maxwell from now on?
Yeah.
If mom's mad, does she call you Maxwell?
Oh yeah.
Yeah.
I
Does she go with the middle? Does she go with the middle name too?
Yeah.
What's the middle name?
Xavier.
Oh man. Maxwell Xavier,
Stop.
do your homework.
Stop. You're triggering the fighter player. Yeah. I told Mrs. Gregerson earlier this year that I went by Well instead of Max, and she believed me. She's wrong all this time.
Well.
I was like, no.
Well.
Just kidding.
Mr. Lavis.
She's too
His
high.
initials are WMM.
M and F.
MXM, yeah.
All right. So logarithmic differentiation. Now, when I perform differentiation on something like this, look at that. I hope we would agree that just to differentiate it, I know how to differentiate this. Every piece in there, I know how to differentiate, right? There's nothing in there that I'm too scared of. However, there's just a lot going on. Like, for example, let's kind of break this down. Look at the numerator of the quotient. I've got a product rule within the numerator. And one of the pieces of the product, I would have to apply the chain rule to, right? So, and then I've got a quotient. So I have to start with the quotient rule. Within the quotient, do a product rule. Within that product rule, do a chain rule. And then look at the denominator of the quotient. That's another chain rule. So while there's a lot going on, would it be impossible? No, we could do it if we wanted to, but it would take a while. Let me show you a technique that would actually help us a little bit more along the way. Okay. Just as a reminder, because we're going to need this here in a second. If I have log of A times B, what is that equivalent to? If I multiply within the logs, what can I break that up into? Log A plus log B. Log A plus log B, right? But base whatever. What about log A over B? Minus, right? Log A, that's a big A, minus log B, right? And then remember, if I've got log A to the P power, what can I do with that P? Bring it out front. P times log of A, right? That's algebra 2. You better go back and thank Mr. Grubb for all that. All right.
I don't think.
So we all remember those, right? We all remember our rules about logarithms, right? Now, what is the easiest logarithm to differentiate? Log base E, ln, right? Log base E. So here's what I'm going to do. I'm actually going to apply the logarithm to both sides because a logarithm is essentially an operation, right? So I'm just going to operate on the same side, or with the same thing on both sides of the equation. So I can do that. I'm not like changing the equation at all, as long as I do what I'm going to do to both sides. So I'm going to say ln of y, and then take ln of the entire other side. X to the 3/4 times the square root of x squared plus 1. And then 3x plus 2 to the 5th power. Okay, let's kind of keep breaking down that right side. Okay? Because what essentially, think about this. I've got a multiplication going on, right? So I can take ln of y is equivalent to ln of x to the 3/4 plus ln of the square root of x squared plus 1 minus ln of 3x plus 2 to the 5th. Right? Does everybody see what I did there? I just changed all multiplication into addition and changed that division into subtraction. And I can keep going with this. Okay, ln of y is equivalent to, what can I do with that 3/4? Pull it out front. So 3/4 of ln of x plus, now, what is the square root? What power? A 1/2. So I'm going to do this, 1/2 of ln of x squared plus 1 minus 5 ln of 3x plus 2. And now we're going to differentiate it. And you may be thinking, wait, you made this way harder. Well, I hope that process was kind of easy, just using the process of logarithms. You guys seem to recall the operation with logarithms pretty easily. Now, you may be thinking, well, isn't it more difficult to apply the differentiation on the natural log? No, remember, it's really easy. I'm going to deal with the left side in a second, but this would be 3/4. What's the derivative of ln of x? 1 over x. So 3 over 4x. Plus, remember that if I've got a chain rule type thing going on, right, I can take the derivative of the inside divided by the original. So what's the derivative of x squared plus 1? 2x over 2 times x squared plus 1. I know I can reduce that too in a second. And then we have minus 5 times, what's the derivative of the inside? 3 divided by the original, 3x plus 2. Now, is there something acting on y on the left side? Yes. And that's where this makes it a little bit trickier. I would love to just leave it on the right side. I would love to just say that's the derivative, but I can't because I did an operation on y. So it kind of turns into this whole implicit differentiation thing. What's wrong?
I'm just asking, can you go over how you did the 1/2 ln of x squared?
Yeah. So I just took the 2 on the bottom. There, that's where the 2 came from. And then to differentiate ln of something, you take the derivative of the inside divided by the original inside. So that's where the 2x over x squared plus 1 came.
Okay.
The 2 over 2 was just from the 1/2. Does that make sense? Same type of thing here. The 5 just went on top. And then I take the derivative of the inside, which is 3, divided by the original, 3x plus 2. Okay, now, so we've got this ln of y on the left side. If I go to differentiate ln of y, it's almost like that implicit differentiation thing where I have to find the derivative on ln, then like a chain rule, and then differentiate y, which ends up being y prime. So this is actually 1 over y times y prime. Why is it that? Well, because remember, think about it. If this is ln of y that I have to differentiate on the left side, peel back the layer of the ln, and I have to write 1 over that thing, 1 over y in this case. Then I can write the y prime. Then I differentiate y and call it y prime. Now, the only thing left to do is multiply by y over to the other side, because I want to get y prime alone on the left side. So when I do that, I'm going to get y times this entire thing, 3 over 4x. I'll reduce it now into x over x squared plus 1 minus 15 over 3x plus 2. Now, I would really not like to leave that as an implicit function because we don't need to. What is y? This big bad thing, right? So let's put that back in, because then on the far right side, we will just have x to the 3/4 times the square root of x squared plus 1, all divided by 3x plus 2 to the 5th, all multiplied by 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that's where I'm going to leave it. I could distribute in and try to get common denominators, but again, that's kind of where the calculus of this stops. The rest of that is just algebraic work. Yes, sir.
When can we use this?
Well, okay, so what would we use this for? This is like saying if you had that function, that is equivalent to finding the slope at any point on that line, right? So if you have this some weird wacky function, I can, with only needing an x value, I only need I don't even need the y value, only by taking an x value. Say I wanted to find along this function at point 7, and when x equals 7. At point x equals 7, on that function, I could find the slope at any given point, instantaneous slope, just by plugging in 7 everywhere for x. And that would give me what the slope would be. It would take a minute because there's a lot of different pieces and parts, but I would be able to tell what the instantaneous rate of change would be. That makes sense? Now, when in real life, what is real life anyway? Right. So this is just to kind of summarize our steps in logarithmic differentiation. First step would be to take the natural log of both sides, and that's really what makes this a little bit more simple. Yes?
Mr. Laverick, we were kind of getting at, like, when would you multiply both sides by natural log?
Oh, when would I use this in terms of like?
Yeah. When would you multiply both sides by ln?
That's what you meant with that question. You could do this anytime. Like anytime you want. Take our most simple equation, like x squared plus 2x, right? I could, or actually just, I should write it like this, times x plus 4, right? Let's even make it simpler. I'm trying to make a good example for you. You know, could I just say this was x to the 7th, so 7x to the 6th? Yes, that's totally fine. But if I wrote this, and I took the natural log of both sides, ln of y is ln of x squared times, times x to the 5th, right? And then I said, okay, well, that's ln of y is equal to ln of x squared plus ln of x to the 5th. Bring it out front. ln of y is equal to 2x. Oh, sorry, not 2x, just 2 ln of x plus 5 ln of x, right? And then I said, now let's differentiate. Now let's differentiate. Okay, that's 1 over y. Y prime is equal to 2 over x plus 5 over x. So y prime is equal to y times 7 over x. Well, what was y? Y was x squared x to the 5th times 7 over x. So look, I'm taking away 1x. Essentially, x to the 7th subtract 1, x to the 6th, and there was a 7 on top, so it becomes 7x to the 6th. So you could really use this whenever you wanted. I mean, that's a really convoluted way to get the derivative, but it works, right? Does that same simple process work here? Is it so simple to just find the derivative of that? No. Did I simplify it a little bit by taking the ln? In my opinion, yes. Does that make sense? Let's do, so I think we were here. Okay, so remember the steps for taking the, finding, for logarithmic differentiation. First thing, take the natural log of both sides, differentiate implicitly, like we did, we said ln of y, or sorry, 1 over y, y prime, and then solve the resulting equation for y prime, okay? So those are the steps for logarithmic differentiation. Apply the natural log to both sides, use implicit differentiation, and then solve for y prime, okay? I don't know why the power rule is still stated there. We've got all these sorts of rules. Let's do one more example. I'm not going to talk about that last slide. Let's just do this last example. Differentiate y is equal to x radical, or sorry, x to the radical x. Now, for that last problem, I had said, you know, would it be easier to find the natural log of both sides and use logarithmic differentiation? In this one, can I possibly find the derivative any other way? Like for this one, I mean, maybe we would take, you know, bring that down front, and then this would be, maybe. But then I've got another chain rule, so I would have to multiply. I don't know. But you know what's easier? Just taking the natural log of both sides. Okay, and I'll show you why. So this is ln of y is equal to ln of x radical x. So to simplify that a little bit, let's bring the radical x out front. ln of y is equal to radical x, ln of x. That simplifies things a little bit more for me. Okay, so now let's find the derivative. So this is really ln of y is equal to, I've not taken the derivative yet, x to the 1/2 ln of x. Remember, I like to put it in terms of rational exponents, any radicals and rational exponents. So now let's take the derivative. That would be 1 over y, y prime. Remember, it's 1 over y, y prime, because the derivative of ln is 1 over that thing, and then the derivative of y is y prime. Now, let's find the derivative on the other side. So this is a product rule, right? This is a product rule. So what we have to do is take f prime g plus g prime f. So f prime g, 1/2 x to the negative 1/2 times ln of x plus, okay, the derivative of ln which is 1 over x, times the original x to the 1/2. Let's reduce that right side before bringing over the y. So 1 over y prime. Okay, so this would be 1 over, this chunk would be 1 over 2 radical x, right? This piece right in here would be 1 over 2 radical x. And now let's apply the ln to it. I'm going to make that 1 into an L. So it's ln of x over 2 radical x. Now take a look at this piece. Isn't this just x to the negative 1 times x to the 1/2? So what does that turn into? X to the negative 1/2, right? Negative 1 plus 1/2 is negative 1/2. So that would be 1 over radical x. Okay, still reducing the right side. Okay. Let's multiply top and bottom by 2 over here to get common denominators. So this would be 1 over y prime, ln of x, 2 radical x, plus 2 over 2 radical x. And now I've got common denominators. So ln of x plus 2 over 2 radical x. Let's solve for y prime now, because I've sufficiently reduced down. That seems pretty good. So y prime is equal to y times this whole thing. Ln of x plus 2 over 2 radical x. And now let's go back in and substitute back in for y. Well, the original problem, y is x radical x. So this is all said and done. X radical x times ln of x plus 2 over 2 radical x. There's my derivative. I think I would have been very wrong if I tried to find any sort of other way to find the derivative. Like we started out by taking the radical x, bringing it out front, subtracting 1. Yeah, I don't think I would have ever come across an ln. Okay. So that was really the only way to find that one. That was the only way to find the derivative there. That's all we could have done. Okay. So again, logarithmic differentiation is just a unique way to differentiate. I believe on the quiz I say use logarithmic differentiation to solve this one. Okay, I direct you to using logarithmic differentiation. All right, that's where we're going to stop today. Let me turn off the video and I can pull up the new assignment. So just as a reminder,